discussing about quasi-convex functions, and now we are going to see a first-order characterization of quasi-convexity. So for a differentiable function, which is the condition on the gradient of that function equivalent to quasi-convexity. Okay? So the situation is as follows. We have an open convex subset of Rn. I need openness because I want to consider differentiability everywhere. And we have a function defined on f. And we assume it to be differentiable. So the question is, f is quasi-convex. If and only if, what? In terms of the gradient of the function. Let us recall first what's the situation with convex function. So suppose we have the same situation here. What are the conditions for it to be convex in terms of the gradient of the function? So, as probably you all know, the condition is that the graph of the function is above the graph of every hyperplane to the graph, which means that f of y is greater than or equal to f of x plus the gradient of f at x times y minus x for every xy in C. Okay? Well, the situation here is different. The situation here is for every xy in C, such that f of y is less than or equal to f, of x, one has the gradient of f of x inner product y minus x is less than or equal to 0. Okay? So compare, the situation here is, graphically is this one. The tangent line, every tangent line is below the graph of the function. There, what we are saying is that if we have 2 points, y and x, and the value of y is smaller than the value of x, then this expression, which coincides with the directional derivative of f at x in the direction y minus x, is non-positive. This means that in this situation, the tangent to the graph should go downwards in this direction, or at most to be horizontal. Okay? I mean, it cannot go up. It's quite intuitive. because then it would have to go down and this would contradict quasi-convexity. That's the idea. And before proceeding to the proof, let us observe that this condition is easily seen to be implied by this condition, as it should be, because convexity implies quasi-convexity. Because in this situation, if f of y is less than or equal to f of x, from this inequality we immediately deduce that gradient of f of x, scalar product y minus x, is less than or equal to 0. Okay? But let us see the proof of this result. In one direction is trivial, in the opposite direction not so much. The trivial direction is this one, because assuming that f of y is less than or equal to f of x, what can we say about this scalar product? As I already mentioned, this is the directional derivative of f at x in the direction y minus x. So let's write the expression for the directional derivative. This is the limit as t goes to 0 of f of x plus t times the direction minus f of x divided by t. But t goes to 0. So for t small enough and positive, t is between 0 and 1. And then what we have here is a convex combination of x and y. And by quasi-convexity, which we are assuming, this convex combination is less than or equal to the maximum of f of x and f of y. But in this situation, the maximum is f of x, which means this difference is negative. And we are considering t positive. So divided by t, this would be less than or equal to 0, as was to be proved. The converse implication is a little bit more complicated, but not too much. It's two-sided because we are assuming differentiability. But, I mean, I am restricting myself positive t. If t is negative, I cannot say this is a convex combination of x and y. Okay, so I'm considering t positive, going to 0, and if it is going to 0, eventually it is between 0 and 1. And then we have a convex combination. Then let us see the converse. I have convexity. Assuming that this first order condition is satisfied. So, take 2 points in C, lambda in 0, 1, assume that f of y is less than or equal to f of x without loss of generality. One of the two is larger, so I consider it to be x. And then, so I have to prove that f of 1 minus lambda x plus lambda y is less than or equal to the maximum, which is x. But we proceed by contradiction. So assume it's not the case. Assume that it is greater than f of x, and then we will get a contradiction. So to this aim, I consider an auxiliary one-variable function, which I'm going to call phi of t for t between 0 and 1 is this expression, 1 minus t x plus ty. Okay? This function is differentiable because f is, and its value at 0 is f of x. Its value at lambda is f of 1 minus lambda x plus lambda y. So phi of lambda is greater than phi of 0. Now I'm going to consider the largest value of t for which f of t is equal to f of 0. So formally, I define t bar as the supremum of t between 0 and 1 such that phi of t is equal to phi of 0. There is at least one t satisfying this, namely t equals 0. And not every element in the interval satisfies this equality, because for t equals lambda, we have that they are different. Okay? So I'm considering the supremum, t bar. So the supremum, t bar, must be, actually the supremum is attained by continuity. Okay? T bar would be a limit of t's for which f of phi of t is less than is equal to f of 0. Then by continuity, phi of t bar is equal to 0, and t bar belongs to the interval 0, 1, but it's different from 1. Okay. Now, I apply the mean value theorem for phi in the interval t. Sorry, this is correct, but it's also more correct if I write lambda instead of 1. Okay? I'm working in the 0 lambda interval. So better I should write here lambda. Otherwise it's not correct. Okay. So I apply the mean value theorem to phi in the interval t bar lambda. Then I get the existence of mu strictly between 0 and lambda, such that phi prime of mu is equal to phi of lambda minus phi of t bar divided by lambda minus t bar. Okay? This is simply the mean value theorem. And remember that this is phi of t bar. So this difference is strictly positive. Derivative is strictly positive. On the other hand, what can we say about phi of mu? We can say that it is strictly larger than phi of t bar, because if it were smaller, I mean, it cannot be zero, phi of mu, because mu is larger than t bar. Sorry, I said I am applying the mean value theorem to this interval, not to the zero lambda interval. So mu is strictly larger than t bar, and t bar was the largest number where phi vanished. So this cannot be zero, but cannot be negative, because then by the intermediate value theorem between mu and lambda, there would be a where phi would vanish, which contradicts that t bar was the largest value in this interval where phi vanished. So we conclude that phi of mu is greater than phi of t bar, which is phi of 0. Well, and now what do we have? What can we do with all these ingredients? First of all, to compute the directional derivative phi prime of mu. I mean, this derivative, which is nothing but the directional derivative of this function at the point y minus mu x plus mu y. So this is nothing but the inner product of the gradient of f at 1 minus mu x plus mu y times the direction, I mean, which is y minus x. Okay? But we have proved that phi of mu is greater than phi of 0, which means f of 1 minus mu x plus mu y is greater than f of x. And now it's the time to apply this condition. When I have an inequality of this type, we know the conclusion with the gradients. So now yx are x and this convex combination, effectively. Okay? So the conclusion is the gradient of f at this point times, here it was y minus x, so here it should be x minus 1 minus mu x plus mu y. So this inner product must be or equal to 0 by the assumption. But now you compute this difference. This is mu I think there is a mistake with the signs. No, no mistake. Mu x minus y, or there is some. Okay. I think there is a problem with signs indeed, because I have to subtract x minus, so this is what I get. And then I would get no contradiction, but there is some contradiction. So there is a sign mistake, which I will try to locate. Strange. Can you locate any sign mistake? When I differentiate t, this is correct, and this is positive. But now what I'm getting here is mu times x minus y less than or equal to 0, which does not contradict anything, because here is x minus y, and here is y minus x. There must be a sign mistake. Phi of mu is indeed greater than f of x. Yes. Then? Yes. You are looking at here? So I'm taking the gradient of the point with a higher value times the smaller minus the largest. So is it correct? But it does not produce any contradiction, because now I notice that I had the same mistake here. Okay, so maybe it's better to postpone to solve this in order to not to waste too much time. This issue, I will look at it later, and I will try to see where is the mistake. But it's x minus y, and there is y minus x. I'm sure this idea is correct, but for some reason there is a mistake in the sign somewhere. Okay, let us try to not to waste our time, and I will tell you the solution tomorrow, hopefully. Okay, but so just to see an example. The function that we considered this morning sorry? Fi is less than or equal to fx, yes. Yes? Yes? You are, thank you. This is the solution. Very much. Yeah. So, there was a step, and then instead of comparing with x, we compare with y. So here we write x instead of x, and then here it is 1 minus mu y minus mu y minus x. So here I get 1 y minus x, and here I get 1 minus mu, which is non-negative, and now this is contradiction. Thank you very, very much. You saved me a lot of time. Thank you. So, the function we considered this morning on the non-negative orthant, but now I need an open set. So I consider the strictly positive quadrant. Is this function. Okay? So, the gradient of this function is the vector minus y minus x. So this condition, I will change the notation, but now x, y are variables, here are points. So instead of x, I will consider x bar, y bar, and instead of y, I will consider xy. Okay? So this condition, written as an implication, reads minus xy less than or equal to minus x bar, y bar, implies this inner product, which would be minus y bar, x minus x bar, minus x bar, y minus y bar, less than or equal to 0. I mean, if we checked this morning that this function is quasi-convex, it was very easy. But let's try to apply the first order condition to check that this function is quasi-convex again. So we should prove that this implication holds true, which is the same as saying here that minus y bar x, so this is equal to minus y bar x minus x bar y plus twice x bar y bar, we should prove that this is less than or equal to 0. X bar and y bar are fixed. X, y are variables. So we have to prove that on this set of points x, y satisfying this inequality, this is less than or equal to 0. But this, as a function of x and y, is a linear function. So we have to maximize this function over this set. We can do it very easily by using Kuhn-Tucker theorem, Kaykitty theorem, or whatever you want. And then it turns out that the optimal solution is at x equal y bar and y equal x bar. So here the maximum is attained. This means this is less than or equal to minus y bar times the optimal x, which is y bar, minus x bar times this y, which is x bar, plus 2 x bar y bar. And this is simply x bar minus y bar to the square with a minus sign. And so it is indeed negative. So we have checked again the convexity of this function using the first order characterization of quasi-convexity. And then, so the last result I want to present about quasi-convex function is that similarly to convex functions, which are the suprema, if they are lower semi-continuous, of affine functions, here the same happens with lower semi-continuous quasi-convex functions with respect to lower semi-continuous quasi-affine functions. So the situation is very beautiful in my opinion. We have the following situation. Convex and concave is affine. Okay? Quasi-convex and quasi-concave we call it quasi-affine. Now, convex and lower semi-continuous for proper functions, functions that do not take the value minus infinity, or that they are identically minus infinity in my definition. So for such functions, convex and lower semi-continuous is supremum of affine functions. Here, quasi-convex and lower semi-continuous is equal to supremum of lower semi-continuous, prefer to write equal, quasi-affine functions. So there is complete symmetry. Well, there is no complete symmetry because here I needed to write lower semi-continuous, but not here. But nothing happens if I write lower semi-continuous here because affine functions are automatically continuous. But there I need to write lower semi-continuous because quasi-affine functions have no continuity property. They may fail to be lower semi-continuous. So let us prove this result. I will not write the statement, but the statement is implicit there. So a function defined on a convex set is quasi-convex and lower semi-continuous if and only if it is the pointwise supremum of a collection of lower semi-continuous quasi-functions. The if part is trivial because if I have a supremum of lower semi-continuous affine functions, they are quasi-convex. And we have seen that the supremum of quasi-convex function is quasi-convex. Also, the supremum of lower semi-continuous function is lower semi-continuous because of the property we saw this morning on level sets. The level sets of the supremum are the intersection of the level sets. So if each level set individually is closed because the function is lower semi-continuous, then the level set of the supremum will be the intersection of closed sets, so it will be closed. Okay, so let's say from right to left, there is nothing to prove, it's immediate. Supremum of quasi-convex is quasi-convex, supremum of lower semi-continuous is lower semi-continuous. The interesting part, which is not difficult to prove at all, is that if you give me a quasi-convex function, then I can find a collection of lower semi-continuous quasi-affine functions, the supremum of which is your function. So we have a convex set and a quasi-convex function, extended real value if you want, which is quasi-convex and lower semi-continuous. So in fact we can consider the class of all the lower semi-continuous quasi-affine minorands of F. And then we will prove that the supremum of this class is F. In which way? Given any point in C, I will prove that f of x is the supremum of the values that all lower semi-continuous quasi-affine minorands of f take at x. Okay? So, consider any number alpha smaller than f of x. So the strategy will be to define a lower semi-continuous quasi-affine function which is less than or equal to f everywhere and which at this point will take the value alpha. Do you agree that this will prove the statement? exist at the end if you don't see it clearly. But for the moment, let us do that. So I take any alpha smaller than f of x. This means that x doesn't belong to the lower level set of f corresponding to the level alpha. And now I'm going to use something that maybe Dr. Laja will tell us later on, the separation theorem. Are you going to talk about the separation theorem? Okay. Okay. So he will explain probably in more detail, more clearly, but the idea is that a set is closed and convex if and only if it is an intersection of closed half spaces. In other words, you have a closed convex set and a point not belonging to it, then you can find a hyperplane that separates in this sense. Sorry? Strictly separates. So the set is on one side of this hyperplane and the point is on the other side. Okay? Or the set is in this half space and the point is in the opposite open half space. This is equivalent to saying that our set is an intersection of half spaces. And this is if and only if, because closed half spaces are convex and closed, so their intersection is convex and closed. So a set is convex and closed if and only if is an intersection of closed half spaces. Let me make a question. Do you have a similar statement in Rn removing closeness? So a set is convex. Forget closeness. If and only if is an intersection of a special kind of set. Well, if you are curious to know, I will tell you later, but now it's not the point for this proof. So, this normal vector to this hyperplane is x star, and so this is the hyperplane has the equation x star x equal k. Okay? So because of this, there exists such a hyperplane, there exists x star in Rn, different from, and there is k, a real number such that this half space, it's better to change a little bit the notation. So instead of x, I use x bar, okay? And then such that every point in the lower level set belongs to that half space. This means x star x is less than or equal to k for every x in the lower level set, okay? But x bar, which is this point, is not in this half space, so it satisfies x star x bar strictly greater than k. Now, how can I use this separation to define the lower semi-quasi-affine function I need? A very simple way is the following. So let's call G the function from C into the extended reals, defined by G of x equal to minus infinity on this half space and G of x equals alpha on the complement of that subspace. this function is less than or equal to f everywhere. Why? If you consider a point in this half space, there is nothing to prove, because at this point g takes the value minus infinity, certainly smaller than the value it takes at f, or equal. Now, if x star x is greater than k, then this x is not in this lower level set, because all points in this lower level set satisfy the opposite inequality. So I want to write everything. First case, if x star x is less than or equal to k, this is the case I already considered, then g of x is minus infinity, which is less than or equal to f of x. Now, if x star x is greater than k, then this x does not belong to the lower level set of level alpha. Okay, which means f of x is greater than alpha. But for this case, satisfying this condition, alpha is precisely the value of g of x. So in both half spaces, in both complementary half spaces, g takes a value smaller than the value that f takes. So this proves my claim that g is everywhere less than or equal to f. Then I also claim that g is quasi-affine, both quasi-convex and quasi-concave. Let's look at the lower level sets. The lower level sets, let's say L of g beta. Beta is a level. If beta is smaller than alpha, what is this lower level set? If I want g of x less than or equal to beta, since g only takes these two values, and beta is smaller than alpha, then g has to take the value minus infinity. This means we are in the half space. So this lower level set is this half space. A closed half space, a closed convex set. If beta is greater than or equal to alpha, what is this lower level set? What is? If beta is greater than alpha or equal, then at every x, g of x is less than or equal to beta, because g of x is either minus infinity or alpha. In both cases, less than or equal to beta. So every x. In this case, the lower level set is the whole space, a closed convex set. So this shows two things, that G is quasi-convex and lower semi-continuous. The lower level sets are convex, then the function is quasi-convex, and closed, then the function is lower semi-continuous. But now we will see that it's also quasi-concave. Look at the lower level sets. We have to make an analysis like here, similar to this one. upper level set of F corresponding to beta. Then if beta is less than alpha, what is the condition? Then f of x greater than or equal to beta g of x. I'm considering the upper level sets of G. G only takes two values, minus infinity and alpha. So greater than or equal to beta must be alpha. Then in this case, U of G beta is half space. An open half space convex. In fact, this also holds with equality here. Now, if beta is greater than alpha, what is the upper level set? So where does G take a value greater than or equal to beta if beta is greater than alpha? Never. Because the values it takes are minus infinity and alpha, which are both smaller than beta. So in this case, the upper level set empty. So convex. Okay? So this function, which I constructed, very simple function, is quasi-affine. It's both quasi-convex and quasi-concave. And it's also lower semi-continuous. And now, so that situation is as follows. So given x bar and alpha, I succeeded to construct a function. If you want, you can call it g of x bar alpha because it depends on x and on alpha, which is a minor Anton f and is quasi-affine and lower semi-continuous. And the value takes this function at x bar. Well, unfortunately, I erased the definition of the function, but probably you have it in your notes. So what is the value that function takes at x bar? I recall the definition. G of x bar alpha at x equals x star equals minus infinity if x star x is less than or equal to alpha to k, and alpha if x star x is greater than k. And what do we know of x star and k? X star k was the separating hyperplane, and we had that x star x bar is greater than k. So x bar is in this zone. So for x bar, the value of g is alpha. Do you agree that this fact proves that our function f is a supremum of lower semi-continuous quasi-affine functions? Probably you don't. Then I will do it more formally. So I consider the class, let's say, F or Q of all the class of all lower semi-continuous quasi-affine minorans of F. Okay? And I consider the supremum of all these functions. Supremum of G for G in K. This supremum is clearly less than or equal to F, because it's a supremum of minorans. But given a particular X or X bar, this supremum applied to X bar is greater than or equal to a particular value. And the value I am going to consider is that G that we constructed. Okay? So this is the supremum over all functions in Q, and this function is in Q. This is said here, that this function is in Q. Okay? That this supremum is greater than or equal to G of X bar alpha at X bar, which we saw to be equal to alpha. And now that's it. No, because alpha is any value smaller than f of X bar. So again, the argument we have used repeatedly, if you have a number which is greater than any number smaller than another number, then you have the inequality. Or again, let's alpha tend to f of X bar, then you will get this inequality with f of X bar, which is the opposite inequality here. So we have equality. So every lower semi-continuous quasi-convex function is the supreme of all its lower semi-continuous quasi-affine minorans. Is this clear? I could tell you more about these things. First of all, that I gave this statement for simplicity, but it's not my favorite statement. Why? Because lower semi-continuity is not the most appropriate notion to deal with quasi-convexity. I told you this morning that in the field of convexity, the king, in my opinion, is Jean-Pierre Crouzet. We are good friends. And he wrote very important and nice results about duality for quasi-convex functions. but they were very complicated. And he told me once that this was his mistake, that he was trying to follow exactly the same pattern as in Rockefeller duality for convex functions, in which lower semi-continuity is crucial. But in quasi-convexity, no. The most appropriate notion to deal with quasi-convexity is the notion of even quasi-convexity, which we will discuss sometime later, but we don't need it. So in fact, the statement I would like here is evenly quasi-convex here and evenly quasi-affine there, but I don't give you this definition of even quasi-convexity now. Okay, but maybe later we will discuss about this. And some results I obtained in the past. So what is the structure of quasi-affine functions? So if I give you a quasi-affine function, can you tell me what is the structure? Okay, even if I don't like, I'll tell you in the case of lower semi-continuous. A quasi-affine function is a function of this type where h is a one variable function which is non-decreasing and lower semi-continuous. For evenly quasi-convex would be non-decreasing, just non-decreasing, because this is automatic. So, lower semi-continuous quasi are simply compositions of non-decreasing linear functions. This is not difficult to prove. Okay? Affine functions are a particular case where h is of the type h of t equal t minus b, a constant, because then you get x star x minus b. This is the expression of an affine function. So this is more general. Okay. So I think it's the time, no? Okay. So we stop here.